Okay, so this is TMUA 2021, paper number 2, 20 questions, 75 minutes. You've got to work pretty quickly. Let's get straight into it. First question is just a simple integration. Change these powers to be fractional or negative so you can actually integrate. I'm not going to go over this in any real detail because if you're taking TMUA seriously, you should know how to integrate and you should know how to substitute negatives in and you should get the answer. Question number 2, immediately more interesting. You've got two coordinates here, 0, 2 and 4, 0. And you're told that those are opposite sides of a square. So if those are the opposite corners of a square, the square must sort of be diagonally sort of across like this. But more importantly, what I can do is I can link those 2 points together and say the square's diagonal must, this is one of the diagonals of the square, the other diagonal must be perpendicular to that and go through that same midpoint. So all I need to do is say, well, the gradient of this line here is well, the midpoint of it is 2, 1, I guess, 2 across, 1 up, because it's 2 down, 4 across. And the gradient is minus 2 over 4, which is minus a half. So the gradient of this perpendicular one is 2. So the equation of this line, which goes through B and D, which will be around here, will be y equals 2x plus c, where it goes through 2, 1, and then you can find out c, and you can say it's going to be this thing here. Cool. Number 3, sorry. Students chosen randomly from class. Each student is equally likely to be chosen. Which of the following are necessary for the student who wears glasses to be equal to 4/15? Exactly 11 in the class do not wear glasses. Not necessary. If you double up this fraction to say 8 over 30, then you've got 22 non-wearing glass members. So definitely not necessary. You can simplify fractions. You learned that in year 2. The number of students in class is divisible by 3. Now this is slightly more, I don't know, I can't think of the word. Slightly more difficult, but I guess when you simplify fractions, this is 4 over 3 times 5, obviously. When you go up or down fractions, simplifying or unsimplifying, you have to multiply them top and bottom by the same number. So all of these are equivalent fractions because they're multiplied by 2 over 2 or 10 over 10. But you can't get rid of this 3. So the total number, which is on the bottom here, the number of students in the class, that's always divisible by 3. You can't remove it. There's nothing to cancel with it up top. I mean, you can add in a 3 times 3, but you still can't get rid of this one. So yeah, this is definitely necessary. And then this third one, the class contains 30 students, 8 of them who wear glasses. Completely unnecessary, because again, you could have a class of 15, and then 4 of them wear glasses. So yeah, only the second one is necessary. And sure, question number 4. This is quite interesting. A is a factor of BC, then A is a factor of B, or is a factor of C. A couple of interesting things about this. Firstly, here's A. So let's just go through this in sync then. So BC here is 200, and A is definitely a factor of 200. But also A is a factor of 10 and of 20. And this is where we learn something about TMUA papers, which TMUA considers OR to be and or. They consider both and or there. So I thought this was actually a counterexample because it's a factor of both, but then I looked at the answers and it turns out that it's not a counterexample because TMUA considers this word or to mean and or. So this isn't a counterexample. This is because A is a factor of 16, which is 4 times 4, but 8 is not a factor of 4 or 4. So this is a counterexample because it doesn't do either of them. And this is not because 6 is a factor of 12 and is a factor of 84. So these two are not counterexamples, but this one is. Just remember that whole idea with the or. You actually see it twice in this paper, where or doesn't really mean or in a computer science sense. It just means it and or. Kind of interesting. Anyway, that's why we do past papers, isn't it? To pick up on these things and their expectations. It actually does say that if you read the logic and proof notes very carefully, but who has time for that? Question number 5. So where has this gone wrong? Well, okay, so you've moved the sign squared over and then you square rooted. You should have done a plus minus. Easy, good. Next question. Should have done a plus minus. Question number 6. So f of x equals 0 for exactly 3 values. So essentially this is saying f of x has 3 roots. And this is saying f dashed of x equals 0 for 2 values means it has 2 stationary points. So we're looking at a graph with 3 roots and 2 stationary points. The first graph that comes to mind might be this cubic here. Or the other way around, who cares? What it's saying is which of these is true? Is P necessary for Q, or is it not necessary, or is it necessary and sufficient, necessary not sufficient? And when you're doing necessary sufficient questions, the way to go is always to think of examples and counterexamples. So can you draw a graph that has 3 roots but doesn't have 2 stationary points, or has 2 stationary points but not 3 roots? So here's the second one of those. This has 1 root and 2 stationary points. So clearly having 3 roots is not necessary to have 2 stationary points, because here's an example of that. So we can cross out the necessary ones. It's clearly not necessary to have 3 roots. Here's that counterexample. What about the other way around? Can we have 3 roots but not 2 stationary points? Well, there's the example right there. That has 4 stationary points, 3 roots. So it's clearly not sufficient. If you're saying, oh, I have a graph with 3 roots, it's clearly not sufficient to say, oh, that has 2 stationary points. So it's neither necessary or sufficient. And the answer will be D. So counterexamples and examples are good for those questions. Number 7, so you've got a circle here, center 9, minus 2, radius 2. Cool. So radius 2, interestingly, means that it tangents the x-axis there. And we've got a square, vertices 1, 0, and so on. I'll draw that. So that's this square here, side length 2, I think. Yep. Okay, and a straight line bisects the area of the square and the area of the circle. Now, to bisect the area of the circle, you have to go through the center. Any line will do it in any direction. As long as it goes through the center, you're bisecting the area. So how do we get a line to go through this center and then also bisect this square? Well, it needs to look a bit like this, and this point here has to go through the center of the square at 0, 1, because to bisect this area, I'm making 2 trapeziums that are rotationally symmetrical around this point here, the center of the square, 0, 1. So yeah, this has to be the point 0, 1, which means, of course, that this length is 1. Now, we've already said that this length is 2. And the question is, where's the x-coordinate of this, where the straight line meets the x-axis? Well, we can see here we've actually got 2 similar triangles. This one is twice as big as this one. So if this length is x, then this length is 2x, because this triangle is just half as big as this one. But of course, this is the point 9 across. So x plus 2x equals 9. So 3x equals 9, x equals 3, and that's the answer to the question, isn't it, actually? The x-coordinate where the straight line meets the x-axis is just 3. Really nice question. Question number 8. Consider the following statement about a polynomial. There exists a number c between 2 other numbers a and b such that the derivative of c is 0, and again, a necessary and sufficient thing. So again, we're thinking of examples. Just to give you an idea what this is talking about, you have 3 points, a, b, and c, and the c bit has the derivative of the function be 0. So the c bit, the function at c is a stationary point. Now, this example right here eliminates a couple of these, because the condition PA, so where the function is at A, equals where the function is at B. Is that true? Well, in this drawing that I've done here, P of A is 0 because it's on the x-axis, but P of B is some positive number. So P of A does not equal P of B, but we do have a stationary point here. So clearly it's not necessary. There's an example that just disproves that. Is it sufficient, though, for P of A to equal P of B? So let's draw a function where P of A does equal P of B. Does there have to be a number in between A and B such that there's a turning point? Well, there does if it's a polynomial. You can think of funky graphs that kind of asymptote between the two and come back to the x-axis, but if you've got 2 functions that are at the same place here, and it's a polynomial, which is a smooth continuous function, it must turn in between the 2 to get to the same place again. So there must be a stationary point in between. So it is sufficient, but it's not necessary because of the first example we came up with. Question number 9. F of x equals this, where p doesn't equal 0. So this is a cubic. As long as p doesn't equal 0, this is a cubic. There is a real number t for which f dash of p equals 0. So this means it's got a stationary point. So just any function with a stationary point. And there are numbers u and v such that this happens. Well, that means that for 2 numbers to multiply to be less than 0, one has to be positive and one has to be negative. So this is saying that the function has some areas below the x-axis and some areas above it. Some areas where the function is negative, some areas where it's positive. That will make it less than 0 when you multiply them together. Okay, and it's saying which of these conditions alone is sufficient to conclude that it has a root, essentially. Now, let's start with the first one. Cubics. Cubics have at least one root. Sometimes they have more, but cubics definitely have a root. That's just a thing that you learn in A-level maths. Statement 1 is sufficient, so we'll cross out all the no's. Then we move on to statement 2. Thinking about functions that have a stationary point, do they necessarily have a root? Is it sufficient to say that has a root? Well, here's a function that has a stationary point but no root. So it's not sufficient to say, oh, if I have a function that does this, then I have a root. That's not sufficient. So we'll cross out the yes for option 2. Narrowed it down to here. Let's think about statement number 3. Now, statement number 3 says that some area of the graph is above the x-axis, some is below. So something is down here and something is up here. Well, if that's the case, then again, for a polynomial, which is smooth and continuous, it must pass through the x-axis to get from here to here. Think about just walking from here to here. No matter what wild route you take, you must cross this line at least once. So yeah, that's sufficient to conclude as a route, and the answer is C. Yes, no, yes. Halfway through, question number 10. A sequence of positive integers, this, consider the statement, if n is prime, let's stop there. If n is prime. If you're in year 13 and you've got some kind of all-school meeting and the head of sixth form stands up and goes, if you haven't filled out your UCAS form, blah, 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 blah. If you have, you stop listening, right? Like, if n is prime means for any n that isn't prime, we stop listening. So the n's that aren't prime are this, this, and this. Don't care about those. N's not prime. Don't care. Then, okay, so we'll get to these ones. Then u of n is a multiple of 3 or is a multiple of 5. And again, here's the or thing. That or does not mean or. It means and or. So we're allowed to be both. That's fine. Okay, so this number here, right? Well, that's both. That's a multiple. Sorry, that's a multiple of 3. This number here is a multiple of both 3 and 5. That's okay. Remember, that's okay. This number here is not a multiple of 3 or 5. So the earliest counterexample of this is u of 5 is 44. Cool, so that just coming up again there, let's remember that. Student attempts the following problem. Show that if this, then this. Okay, so let's just run through this. So, okay, they're squaring it, that's fine, that's squared correctly. Completing the square on this bit means taking away another 2 copies of that, so that's fine. Timesing everything by x squared, y squared, we're allowed to do that because x squared, y squared is definitely positive for real numbers, so we don't have to swap the sign, so that's fine. And then they've made the substitution that was given to them and they arrived here. Except, so all the lines are correct, except they've done everything entirely the wrong way around. If this means you start here, you don't end here. If this, then this, you can't say this is true because that's what you're trying to show. And they've just used it to get from here to here. So everything here is correct, but they've gone entirely the wrong direction, which is this option here. It's incorrect, not because there's mistakes, but because they've gone completely in the wrong direction to do this. Would be correct if written in reverse order is another option, and why wasn't it that? Again, it's not that because just writing in reverse order wouldn't help. Because again, the first line, if you imagine this in reverse order, the first line would be using this idea, and again, that's what you're trying to show. So yeah, you can't just write it in reverse. They've just done the entire thing backwards. Well, I think you understand what I mean. They've proved, if this bit thing had said, show if there exist numbers x and y that do this, then this, they've shown that. So they haven't written out backwards, or just done it the wrong way around. They've pretended the statement is the other way around and proved that, which is this option here. Number 12. Which of the following statements about polynomials f and g is true? If f is bigger than g for all x bigger than 0, then the integral of f is bigger than the integral of g. Now this feels true, and sometimes in TMUA, things that feel true are pretty much all you need. So here's a function where f is always bigger than g, like it's always just higher up than g is. That's just what all that really means, it's just higher up in the picture. And the integral of f is always going to be bigger than the integral of g, because when it's in the positive section, you're just going to get bigger numbers when you integral. And when it's in the negative numbers, sure, you'll get a bigger number when you integrate g, but it will be a bigger negative number, which is still less than. So this is just true. And, you know, there's very complicated proofs of that, but you're in the middle of a TMUA paper. Don't do complicated proofs. Just go with gut feelings and move on to the next question as quickly as you can, because you've got lots of questions to do. Next one, if f of g is bigger than, so the same thing here, then the derivative of f is bigger than the derivative of g. So again, counterexamples here. Examples and counterexamples. Let's come up with a function. There's f of x. Now that's always bigger than this g of x, yeah? Because it's always just above g of x. So it's always bigger. Except the gradient, which is what we're comparing, the gradient of f here is negative, whereas the gradient of g is always positive. So this isn't true. Technically, we're saying for only x bigger than or equal to 0, but here we've got a negative gradient in f, but g is still positive. So this is not true. So that's not always true. Come up with a counterexample. Next one, if the gradient of f is always bigger than the gradient of g, then f is always bigger than g. Lines are good ones here, because here, if I call this f, then the gradient of f is always bigger than the gradient of g, because g is just a negative gradient and f is a positive one. But we can see here g is bigger than f. because it's higher up. So this is not always true, only the first one is true. Counterexamples, examples, counterexamples, drawings, always the way to go. Question 13. Simultaneous equations, which are this, so we're looking for some kind of plane defined by this. So let's draw these. So add x to both sides, and we end up with this. Well, that's very easy to draw. It just looks like this, with this being 3 and the gradient being 1. Add x squared to both sides, we get, oh, yeah, sure. Add x squared to both sides, we get this, which is a quadratic with y-intercept of 1. Looks a bit like this. We can find these 2 points if we want to, if we equate them. I don't know whether this is going too far. By the way, R is below the line and below the curve, so R is all of this area. We could find these intersection points if we wanted to. I'm not sure whether it's necessary, but I did anyway. We find at 2 minus 1, we can substitute those in to find y as 5 and 2. And we're asking which of these is true for every point in R. Is x always between minus 1 and 2? Well, no. Because right over here you have the point 10, 0, and x is 10, and it's in this region. Now, I think this is tricking people who assume that this is the region, but it's not. All of this is, because you're less than both of them. This is complicated, so let's look at this one. Y is less than 5, also not true. Up here we have the coordinate maybe 10, 20, or 10, 15 or something. So y can definitely be bigger than 5, because r encompasses all of this below this line going up there. What about this one here? Again, just try and find a counterexample. There's probably more mathsy, intelligent ways of doing it, but I just picked this point down here and noticed if I did that, x is 0, y is minus 10, I get this. Minus 10 times minus 10 is 100, which is definitely more than 3. And so this point disobeys this, and so it's none of them are true for every single point. Good. Counterexamples. I don't know how many times I've said that. Anyway, simultaneous equations. Immediately, let's just take these away to get this. Cool. And then let's factorize. Now, I've got 2 numbers here multiplying to make 1. This number is always positive, which means that this has to be positive. For the 2 things that you multiply to equal 1, that has to be positive, which means p has to be bigger than 1. So that's one condition. Now let's consider what happens if I eliminate the x's instead of the y's. Or, okay, I can times this by p. This one's slightly more complicated. Then I can take away, and I'll get this. I chose to put the p up here, and then I chose to use the log laws to get y to the p over y, which makes y to the p minus 1. And I also raised both sides to the power 2 to make this. Now, this doesn't really seem like I've got anywhere, and it took me a while to figure out what to do here. But what I eventually figured out, apologies if I just hit the mic somewhere there. What I just figured out was, okay, imagine this was y squared equals this. You would square root both sides. Y cubed, you would cube root both sides. Y to the p minus 1, you p minus 1 root both sides. But that's the same as writing to the power 1 over p minus 1. So I can write it like this. And now this is fine as long as, well, here's a fraction, so as long as the denominator isn't 0, you're fine. So as long as p minus 1 isn't 0, you're fine, as long as p isn't 1. But that's okay, because this condition needed p to be bigger than 1 anyway. So the final condition you need is just anything p greater than 1. This kind of makes sense when you go all the way back to here, where you consider if p is 1, you get 0 here, and then y suddenly doesn't do anything. So that gives you an inkling that p equals 1 doesn't really achieve anything, because it destroys y. You can no longer choose y to be anything that you want, kind of thing. Question number 15. We're getting through it quite nicely now. This question I went down a very dark alley for a while until I realized there was a much easier way of doing it. So here's a circle, and I want it to be tangent to the y-axis. Now the y-axis is the line x equals 0. So if I solve this with the line x equals 0, which essentially just means putting x is equal to 0 into this, which is what I've done, I want this to have one solution. If I want this to have one solution, it needs to have discriminant 0. So, okay, well, I plug that in, and I very quickly arrive at this condition here, which is necessary and sufficient, because the reason it's necessary and sufficient is because the discriminant check is a necessary and sufficient thing. So it kind of leads from that. Like, there's no instances in which this equals 0 and you don't have one root. That itself is a necessary and sufficient check, so we're done. 16. Love drawing some mod graphs. This question is great. So this graph is, whenever you're asked how many solutions something has, graph drawing is the way to go. So let's draw these. Let's draw this graph, px minus q. I'm assuming we can all draw a straight line. Now let's draw this graph. Now that's a bit more complicated, but when x is positive, which is over here, this is just the graph x times x, because mod x doesn't do anything when x is positive. So over here, we're just drawing the curve x squared, which must look like that. Now over here, mod x equals minus x. So over here, we're drawing the curve minus x squared, which is just x squared upside down, which looks like that. And we're asking how many solutions does this have. Well, right now it has 3, so I know there's an instance in which it can have 3 solutions. But all I need to do here is just take this line and move it around a bit and see how many solutions can I get. Well, I can get 1 down here, I can get 2 if I make it tangent, I can get 3 as I said. Now can I get 0? Well, it's tempting for a moment to think that I can by putting it over here somewhere, but this curve just gets very, very steep, right? And so it's always going to intersect that line at some point. And so you can have either 1, 2, or 3 solutions, just based on drawing those. Good, question number 17. Quite a nice question here. We're into the questions that are very difficult. So no worries if you were struggling about these. You'd also have been running low on time as well, I guess. First thing to do is to maybe fix this up. So this is x to the power of a half, of course. We can bring that half down in front of the log. And now this is half times this, so I can actually separate and add them. Like I can say it's log to base 2 of this plus log to base 2 of this, just by separating this. Now log to base 2 of a half is minus 1, because 2 to the power minus 1 is a half. So that makes it a bit simpler, I think. Now I'm going to work on g, again, or I can, yeah, sure. Again, this is the power of a half, and now this is one object, the power of a half, so this half comes right the way out to the front of this log, because it's log of some number to the power of half, the half brings forward. So that actually equals that. And kind of what I'm trying to do here is I'm trying to find when did these graphs intersect each other. Now actually, now that I've got them both looking like this, that's very easy for me to find. I can say, when does this equal that? Well, add half, or take away half log from both sides, add to 1 to both sides, then times by 2, and we find this. Raise both sides to the power 2 to get log to base 2 of x is 4, do it again to get x is 2 to the power 4 is 16. So x is 16. So these meet when x is 16. And you can check that by putting them back in if you want to. Now, what do the functions themselves equal when x equals 16? Well, root 16 is 4, log to base 2 of 4 is 2, log to base 2 of 2 is 1. So f of x equals 1, and so does g of x. Okay, so if we're thinking about just plotting these, I'll make one red and one green so that we can plot them. They intersect at x equals 16, y equals 1. Now, they're both log functions. We know log functions look a bit like this, kind of on their side like this. Now this log function is just a log function that's being shifted down. And the g one is a log function that's been squashed down. Now because this one's been shifted down and this one's been squashed down, the red one is actually going to be slightly taller and actually going to be able to overtake the blue one at this point. So you can imagine you had an original log graph and this one got squashed down to make it less steep. And this one got shifted down, so it's still steeper, but it's just shifted down at all these points. And so this is what the graphs look like. Why am I doing this? Well, I'm doing it because I'm trying to figure out which of these are true. Now they meet at 1. So if we look at all these, the half doesn't really seem to have much to do with it because the half isn't their intersection, nor do the zeros. The 1 seem like the most likely thing to be relevant here because the 1 is the value in which they intersect. And what we can say is over here, 1, which is this line here, is bigger than the blue, which is g, which is bigger than the f, which is the red, which is this statement here. 1 bigger than g, bigger than f. That's over here. And over here, 1, which again is still here, is smaller than the blue, which is g, smaller than the f, which is here. So this statement actually is completely correct. 1 is less than g over here, which is less than f. And here, f, which is red, is less than g, which is less than 1. So this is the true statement. That was a tough question, and I don't know. I don't really know where I was going when I thought to do all this. I just thought it seemed quite natural to find an intersection and maybe do some graph plotting. I mean, it's so often the case in TMUA that you need to do some graph sketching, so that was just what I was aiming for. And then eventually when I did, I stared at this for long enough to figure out what these meant and kind of just got it. But yeah, I think that was probably one of the tougher questions on the paper. Anyway. Student picks a number, x and y here. Let's just pick some numbers. Let's make the sine graph because this is about sine, and let's pick the numbers 0.4 and 0.6 maybe, something like that. What we can read here is that he wants to draw a triangle with AB equal to 1 So he wants the base to be 1, and he wants the angles sine of A to be x and sine of B to be y. So he wants sine of some number, let's just say to be 0.4. Now that looks to be about 20. And sine of some other number to be y, which we've just said is 0.6, which looks to be about 40. And he wants to draw a triangle like this. Is that possible? Of course it is. Base 1, angle 20, angle 40, of course that's possible. Right, there it is. The question is, how are you going to draw another type of triangle? Well, because sine of x equals 0.4 has another solution, of course, over at 160, roughly. And likewise for this. So is there another triangle here that we can use? Well, yeah, I think there is, because if we choose A to be 20 still, but then choose B to be 140, this triangle still works, right? We're just left with 20 degrees left over, and this all obeys this, right? Sine of this is still this, because we've just chosen two symmetrical solutions, and yeah, we've got two solutions. So it's definitely okay, it's definitely possible to have two triangles that are possible to draw. Is it possible to only have one, or even three? And that's what we need to investigate next. And to do this, let's not pick actual numbers, let's think about it algebraically. So let's just choose big A to have to equal some little a value here, which means the other solution is of course 180 minus that little a. And likewise for B, 180 minus B. Now A and B are both less than 90, of course, because if you pick some number between 0 and 1, the first intersection with sine has to be between 0 and 90. So A and B are both less than 90. We'll just choose B to be the bigger one, because why not? Which means both of these are bigger than 90. Okay, and that's really important. The first one is when we just draw base A and B, base 1. That's perfectly possible to draw, because A plus B is definitely less than 180, because they're both themselves less than 90, which means we're not taking away, and this number is definitely positive, because these two numbers are less than 180 together. So this is definitely possible to draw. There's a positive angle there. What about if you chose this with this, or this with this, or this with this, though? Well, this and this clearly won't work together, because these are both bigger than 90, and we can't have two angles in a triangle bigger than 90. But what about, let's say, A and 180 minus B? Well, that would leave this angle to be 180 minus A minus 180 minus B, which is this. And we've said that B is bigger than A, so this is a positive number. So that triangle works. The other way around, though, if you choose this one and this one, the opposite thing happens, where your angle in the corner is going to be A minus B rather than B minus A, and we've chosen B has to be bigger than A. One of them has to be bigger than the other, unless they're equal, which maybe is a case you want to consider on its own, where you choose the equal case. But this is not fine, because A is minus B is less than 0. I'm just thinking to myself, because I can't remember whether I considered this properly or not, what happens if A and B are the same, but they're not. Look, actually they're not, because x and y can't be equal, so we can't choose the same line twice. So A and B are not the same, one has to be bigger than the other. Yeah, okay, that's the logic I must have used when I did this. And so anyway, the answer is you can always have two triangles, but you can't have three and you can't have one. Good, question number 19. This question really tripped me up for a second. Let's do it. So I put the surds together, of course, and then I multiplied out because I saw there would be a difference of two squares. And I also saw that, of course, I can replace those with sine squared and cos squared, which seems great, because then you're just rooting cos squared and rooting sine squared, which of course equals just cos and sine. Now, there's a problem here. And this is what I did the first time, by the way. I just did that. I thought, oh my god, look how juicy this is. This is 2 sine theta cos theta. That's sine 2 theta. I can solve this super easily between 0 and 360, or 1 and 360. There are 3 solutions. Sorry, there are... what on earth is this? Sine of... oh, theta is 90. Yeah, sorry. Theta is 90 gives you sine of 180, which is there, and then you've got another one there. Sure, that's fine. So there are 4 solutions, except there aren't. And here's an example of more TMUA questions. Look at my working. Where is the student's mistake? On which line did the student make the first mistake? Because this is not okay. The answer is not 4. And my mistake is here. No, sorry, it's not here. It's here. Here. The root of cos squared is not cos. In the same way that the root of minus 5 squared is not minus 5, like you might think it is for a second, but then you actually do it and you think, well, minus 5 squared is 25, and the root of 25 is just 5. It's not plus or minus 5. The root is defined to be positive. So you can't just cancel this and this, because minus 5 doesn't equal 5. We can't just cancel this and this. Actually, root of a squared is not a, it's mod a. So actually, I need to replace this cos and this sine with a mod cos and mod sine, like this. And now there's plenty of ways to finish this question off. The way that I did it, I drew the sine and cos graph, which of course I had drawn many times during this paper, so I already had those to hand. I did a similar thing I did in a previous question, which is I considered the cases separately. So if theta is less than 90, both sine and cos are positive. And the mod of a positive number doesn't do anything. So you just end up with this statement, if theta is less than 90. But that statement, of course, turns into the statement we saw before, and that has a solution at theta is 90. Less than or equal to, because of course we can get to 0, and mod of 0 is still just 0, so it still doesn't do anything. So we have one solution when theta is less than or equal to 90. Then I considered, so I just wrote that down. Then I considered between 90 and 180, not including 90 because I already included that. Now between these two, sine is positive, so mod sine doesn't do anything. Cos is negative, so mod cos is minus cos. So I end up with this, but of course these cancel and I get 0 is equal to 0, which is always true. So this is true for every value here, which is 90 values. That's true for 90 values. All the way up, it's always true. Then I considered the next quartet between these two. You do the same kind of idea. These things are both negative there, so you swap both signs, you get this. You could times by minus 1 if you want to. You get the one solution at 270. And then you consider the last quadrant, which is, I should have totally put, I don't know why that says 20. That should definitely say 270. Apologies for that, 270. Both of them are, well, cos is positive, sine is negative, which means, again, you take this one doesn't change, this one does, they cancel, and for all 90 solutions in between here, you get the answer. 90 plus 90 plus 1 plus 1 is 182 solutions. There are other ways to do that question, including drawing the graphs and stuff, but I thought that was quite a nice little solution to it. Very last question here. Again, a question that you need a lot of feel for rather than a proof for. You just need to kind of get a feeling for it and put down the answer, I think. So f of 1 is just mod x. F of 2 is mod x plus x, all modded. F of 3 is mod x plus x, all modded, plus x, all modded. Like you just shove this whole thing into there, and then you have another plus x and then mod it. What I decided to do here was I decided to say, well, let's just see what happens for smaller numbers. I'm supposed to go all the way to 99. Of course, writing these out to 99 and then integrating is not going to be fun. So I just was hoping there was a pattern here. And the answers also suggest that there might be some kind of building pattern going on. So the integral of f of 1 is just the integral of x, because it's just there. Now, mod of x is just this graph, right? Between 1 and minus 1, that's two triangles, each with height 1, width 1. So 1 times 1 times a half is a half, plus a half is 1. So the area of that is 1, so the answer to this is 1. So the integral of f1 is just 1. Integral of f2 is this. Now, again, I sketched this. When you're in the positive area, mod x is just x. So over on this side of the graph, we just have x plus x, which is 2x, all modded, but we're in the positive section, so that's just 2x. So I just draw 2x. Now, when we're in this section, mod of x equals minus x, and minus x plus x is 0. So when we're in this section, we're just a flat line. And what's the area of this? Well, this is the graph 2x, remember. So this is the point 1, 2. So this triangle has area 1 times 2 times a half, which is 1. So that's kind of cool. Maybe the area is always 1. Let's do one more to check. F of 3. So again, think about drawing the graph. In the positive section, mod x is just x plus x is 2x, mod is just 2x, plus x is 3x, mod is just 3x. So we just get the graph 3x just on this side. In the negative section, be more careful here, mod x is minus x. Mod x, so this bit here becomes 0, minus x plus x is 0. Plus x is mod x, but remember mod x is negative x because we're in this section. So actually we do have another line, it's not just a flat line, we do have another line, gradient 1, so less steep than this one in this direction here. And what's the area of that between 1 and minus 1? Well, the area of this is 1 times 3 times a half, which is 3.5. And the area of this is 1 times 1 times a half, which is a half. And 1.5 plus a half is 2. So the area of this is, the integral of f of 3 is actually 2. So we go 1, 1, 2. And now, I did actually draw f of 4. I couldn't be bothered to do it on the computer, but I did draw it to get 2 again. And I figured at this point, all that's going to happen is it's going to go 1, 1, 2, 2, 3, 3, 4, 4. I kind of just hoped that was the pattern. And looking at the answers, it's the only reasonable thing to say that the pattern is going to be. And if that is the pattern, then f of 99 ends up being 50. So yeah, the answer is 50. That's why I went with it. You could prove that if you wanted to by doing some polynomial maths. You have 75 minutes to do this whole paper, so you probably shouldn't. You should probably just plot the pattern and run with it. That's the whole paper. Thank you so much for watching.